Hello everyone, this is Professor Roman. Let us continue the group theory lectures. I want to talk now about the common themes that exist throughout abstract algebra, something I mentioned earlier. For those who have studied various types of algebraic structures, such as groups, rings, and vector spaces, you will recognize that there were several common themes in the study of these structures. You'll recognize after the fact that there were these common themes. For example, in linear algebra, we study subspaces, quotient spaces, and structure-preserving functions between vector spaces, which are known as linear transformations. But similarly, in group theory, we study subgroups, quotient groups, and structure-preserving functions between groups. These are called homomorphisms. And in ring theory, we study subrings, quotient rings, and structure-preserving functions between rings. They're also called homomorphisms. And there are similar common themes in the study of modules, submodules, quotient modules, structure-preserving maps between modules, and lattices. The situation is a little bit different for fields due to the lack of a complete multiplicative inverse operation, because 0 doesn't have a multiplicative inverse. But we still do study subfields and structure-preserving maps between fields. There are no quotient fields. That does not work in the context of fields, the quotient structure. But nevertheless, because of the common themes that run throughout the study of algebraic structures, it seemed to me that it would make some sense to look at those common themes now to give you a perspective for your future study, rather than wait till you've studied these structures and then look back and say, yes, there were these common themes. So for our journey, let's imagine an unspecified type of algebraic structure, which I'll call a widget. So widgets could be any one of the structures in that table I showed you earlier. It could be groups, rings, fields, lattices, so on. But the way to think of a widget is simply as an underlying set upon which are defined some algebraic operations, which we'll call the widget operations, and those operations possess certain widget properties, such as associativity, commutativity, neutrality, inverses, and so on. Okay, now when you first embark on the study of widget theory, the first thing you'll probably encounter is the definition of a widget. And this will be followed by a few of the basic consequences of the definition. So, for example, one common consequence is the uniqueness of identity elements. And we've seen that in the case of these two monoids that we looked at, the monoids of integers. The same is true for inverses. When they're present, they're unique. It's worth noting, however, that the definition of, say, an identity element does not specify that the element must be unique. And the reason is that, generally speaking, definitions should be as lean as possible. You don't want to include items in the definition that are consequences of the rest of the definition. So that's why we don't say in the definition that the identity for a particular binary operation is unique. It's a consequence of the identity property. The next common theme you probably encounter in the study of widgets is the concept of a subwidget. So you have subgroups, subrings, subfields, submodules, subspaces, sublattices, so on. And the idea here is actually quite simple. If S is a non-empty subset of a widget W, then it's natural to wonder whether the algebraic operations, the widget operations that are defined on W, can be restricted to the subset S and thereby make S into a widget in its own right. Okay. If that is the case, and it's not always the case, but if it is, then the subset, together with those restricted operations, is called a subwidget of W. And we'll see an example in a minute. But there is a potential problem. We can always restrict the operations to S, but that doesn't mean that the restrictions are operations on S. So, for example, here's a unary operation F from W to itself. The restriction to S always exists. I use this notation for restriction. But all we know for sure is that it maps S into W, not necessarily into S. And if it doesn't map S to itself, it's not an operation on S. So if you can't write this, that the restriction of F to S maps S into S, you don't have an operation. You have a function, but not an operation. And the same potential problem occurs with the restrictions of nullary and binary operations as well. Now, if the restrictions of the widget operations to the subset S do form legitimate operations on S, we still are not quite done. We still have to verify that the widget properties of these operations on W hold for the restricted operations. Fortunately, this is generally very simple. Just as an example, if a binary operation on W is associative, then its restriction to the subset S is also associative. It's the same equation. If this holds, I'm writing multiplicative notation now, if this holds for all elements of W, then obviously it holds for all the elements of a subset S. So there's nothing to prove, really. Same thing would apply to commutativity. Also, if an identity element, let's call it E, in W is also in S, it'll function as the neutral element or the identity element for S, or for the operations that are restricted to S. Okay. A unary operation, which I'll call lambda, from W to itself, that produces inverses for an associated binary and nullary operation, will still do so even if you restrict lambda to S. So, in summary, if the widget operations on W remain operations when restricted to S, then the common properties, associativity, commutativity, identity, inverses, will still hold for the restricted operations. So even though we have to check that, it's, dare I say, obvious. So let's look at an example. Let's take this additive group of real numbers. Lambda, as always, is the function that takes the negative of a real number. And suppose we restrict these operations to the integers. Do we get operations? Well, we have to check that the sum of two integers is another integer, which it is, of course. And for the nullary operation 0, that it belongs to the integers, which of course it does. And that the negative of any integer is an integer. So these three properties tell us that when we restrict the operations of the additive group R to the integers, we get legitimate operations on the integers. And as we discussed, associativity of addition holds for the elements of Z because it holds for all the elements in R. And 0 is neutral for addition of integers because it's neutral for addition of all real numbers. And the negative of an integer is an integer and has the required properties of additive inverses. These two sums are equal to 0. This holds for all real numbers, therefore it holds for all integers. So this algebraic structure consisting of the subset Z of integers together with the restricted operations, and I'm just using the same notation here. I could have written plus sign sub Z, lambda sub Z, and 0 sub Z, but it seemed a little overblown to do that since Z is sitting right here. It's clear from the notation these are operations on Z, so I didn't think that was necessary. But this is a group. The operations are legitimate and the group properties hold for them. So, by definition, this is a subgroup of the bigger group. Now, on the other hand, suppose we had restricted the operations of this group to the closed interval 0, 1. Now we have problems because the sum of two elements in this subset S doesn't have to be in S. So the restriction of addition to S is not a binary operation on S. Neither is the restriction of the unary operation of taking negatives. The identity actually does belong to the subset S, so that part is okay, but we're far from a subgroup here. As a matter of fact, this is not even an algebraic structure because addition is not an operation on S, neither is lambda. So it's not a group, certainly, and therefore it can't be a subgroup of this group. So totally falls apart. So for the types of widgets that we are going to study in this series, linear algebra, group theory, ring theory, field theory, lattice theory, for vector spaces, for modules, for monoids, for groups, for rings, for fields, for lattices, all we need to do to verify that we have a substructure is to check the following closure properties. First, all nullary widget operations, those are elements of W, have to lie in the subset. This is the easiest one to check, and so it's worth checking first because if this fails, you're done. You can stop. This property is referred to as the closure of the subset S under the nullary widget operations of W. Second, for all unary widget operations, so functions from W to W, the restriction, which looks like this, must map the elements of S into S. And so, in fact, the restrictions look like this. And this is referred to as the closure of the subset S under the unary widget operations of W. And similarly, for all binary widget operations, the restriction has to send S cross S into S. And that's closure of S under the binary widget operations. I should mention that I sometimes hear students say that it is, say in the binary operation case, that it is F that's closed. No, it's not F that's closed. It's S, the subset, is closed under F. Of course, it's possible that a subset S of a widget W can be a widget under different operations other than the restrictions of the operations on W. But that's totally irrelevant to the question of whether S is a subwidget of W. The only thing that's relevant is whether the operations on W, when restricted to S, form operations on S. Another theme that is encountered, perhaps around this time, in the study of widgets, is the issue of making new widgets from existing widgets. One way to create new widgets is, and this applies to many, but there's one exception, fields, but all the other algebraic structures we're discussing, is to begin with the underlying sets and take Cartesian product. So let's say we have two widgets of the same type, two groups, two rings, whatever. So W1, and I've used dot for the binary operation, lambda 1 for the unary operation, E1 for the nullary operation. This is just an example, so I wanted to include at least one of each type of operation, and I see no reason to include more than one because it works the same way. And we have this widget W2. Then we can certainly form the Cartesian product of the underlying sets, this set of ordered pairs. And we can try to define widget operations on this Cartesian product. Now the way that's done is first a product binary operation is defined component-wise. So we have two ordered pairs from this Cartesian product. We just take the product of the first coordinates. So we get S times U, and this is the product in W1, and then we also form the other product, T star V, so that's the product in W2. We can also define a unary operation component-wise. I call that delta. Delta of this ordered pair is lambda 1 of S, comma lambda 2 of T. So we take the unary operations in the two respective widgets and apply them to their elements. And the nullary operation, or a nullary operation, can be defined as the ordered pair consisting of the two nullary operations. Now these component-wise operations, it turns out, will define a widget. The properties, associativity, and so on, will hold. And this will define a widget of the same type as the components. If the components are groups, you get a group. If the components are rings, you get a ring. This works for vector spaces, modules, monoids, groups, rings, and lattices. The only one it doesn't work for from our table of algebraic structures is fields. And the reason it fails in the case of fields is that for a field, it's it can be shown, and it's quite easy to do, that the product of non-zero elements must be non-zero. You, of course, know this for the case of the real numbers. But what happens if we try to, if we define these operations on the Cartesian product, R cross R? Well, look at this product. 1, 0 times 0, 1, we're taking the product component-wise, we get the 0 element, but these are non-zero. So something must have gone wrong in trying to use this Cartesian product structure for fields. It doesn't work. Fields are a little unusual because of that partial unary operation of taking inverses. It doesn't apply to 0, and that really creates all sorts of, let's say, different behavior than you get from vector spaces, groups, and rings, for example. Let me kind of pause and have a sip of tea here. One of the most important ways to make new widgets from old widgets is to take quotients. And quotient widgets can cause a bit of confusion when they're first encountered by budding widget theorists. It's not really that tricky, I think, if you look at it the right way. So here's the idea behind quotient widgets. Suppose that W is a widget. And suppose that we have a partition of W, of the underlying set, okay, into blocks, B1, B2, B3, and so on. There might be a finite number of blocks, there could be an infinite number, doesn't matter. It could be an uncountable number of blocks, makes no difference. Here's a picture of the partition. Now what we'd like to do is use the widget operations on W, on the elements of W, to define widget operations on the blocks of the partition, P, and thereby make these blocks into the elements of a new widget. So just to be clear, the blocks, which are non-empty subsets of W, are to become indivisible elements of a new widget. So we don't look inside the blocks anymore. We treat each block as just an element of the new widget. So let's focus on a binary widget operation, which I'll call the product and note by juxtaposition. How can we define what we might call the block product for this partition? Well, there's really only one way to, I think, one sort of obvious way to try to define the product of two blocks. The only thing we have to work with is the original widget product of elements. So let's say we have two blocks, BI and BJ, and we want to take their block product. We want to define it. Well, we grab an element from each block, BI, little bi and capital BI, and little bj and capital BJ. And we can take the product of those elements in W, BI, BJ. Now, since P is a partition of W, there's a unique block, which I'll call B sub k, that contains this product. So it's important that we're dealing with a partition here. And then we'll simply define the block product, capital BI, capital BJ, to be equal to capital BK. Now that we have, possibly, a product on the blocks, we can ask whether this product satisfies the widget properties and therefore makes P into a widget. Well, just as an example, if this block product, assuming it makes sense, it will be, if the original widget product is associative, the block product will also be associative. And here's the reason. Say we have 3 blocks now. So I've written BI, BJ, BK. That, we're not doing this anymore. This is just 3 arbitrary blocks of the partition. And if we take individual elements from each block, then this block product is equal to this product of elements of W, and now we can use the associativity in W to write this way, and then this is by definition equal to this. So we get associativity of the block product. It kind of raises up to the blocks. And the same thing, we would have to consider also the unary and nullary widget operations as well, see how they work and their properties. But never mind that now, because we'll get to it later, but there's a very serious potential problem here. And it would be interesting to see if you can see it before we continue. You might want to pause the video and think about it a minute. The way we define the block product is ambiguous. Suppose somebody else picks different elements from the blocks. So let's say someone else picks BI prime from BI and BJ prime from BJ. There's no guarantee that BI prime, BJ prime, and our choice, BI, BJ, lie in the same block of the partition. And if these 2 element products are in different blocks of the partition, then this all breaks down. The product of blocks is not well defined. And here is an example. Think about this monoid. Integers under multiplication, identity element is 1. And form this simple 3-block partition. B0 is the set of all integers less than or equal to -2. B1 is these 3 integers. B2 is the rest, integers greater than or equal to 2. To define the block product B1, B2, we grab an integer from each block. So let's say we grab 0 from here and 2 from here. The product is 0. It lies in block B1, so it looks like B1 times B2 is equal to B1. But if instead we take this element from B1, 1, same element from B2, the product is now 2, and that's in B2, so now it appears as though this product should be B2. Well, we have an obvious problem. An ambiguity. This block product is not well defined. It's useless. However, if we can resolve this problem of ambiguity, if we can get to the point where it doesn't matter which elements we pick from each block, the product, the element product will always be in the same block. We've removed this ambiguity. The block product makes sense. And we're going to do that for groups in this course. Then depending on the type of widget we started with, the partition P will be a widget under the block product. So in short, sometimes it works and sometimes it doesn't. When it works, we get this partition becomes a widget, and it is called a quotient widget or a factor widget. And one can say that it is formed by factoring by the partition. So this works to define quotient groups, quotient rings, quotient lattices, quotient modules, quotient spaces, vector spaces, but not quotient fields. Again, we run into a problem, and again, it's in essence because of that partial, not complete, unary operation of taking multiplicative inverses. In case you've studied algebra before, you may have heard the term field of quotients. That's a totally different concept. That is not the same as quotient field, which that concept does not exist, quotient field. Okay. Field of quotients is a way to turn a certain type of ring into a field. So it's a different idea altogether. Another common theme in the study of algebraic structures is that of a structure-preserving function or structure-preserving map between two widgets. So to illustrate, suppose that we have two widgets, W1 and W2, each of which has a binary operation, a unary operation, and a nullary operation. And these widgets are of the same type, both groups, both rings, both lattices, whatever. A function h mapping the underlying sets, W1 to W2, is said to be structure preserving if the following holds. First, as to the binary operations, we have this equation. And what this says is that if we take two elements in W1, we take their product and then apply the function h, we'll get the same result as if we first apply the function h to each factor and then take the product. Of course, the product here is in W1 and the product here is in W2. So this is, in a way, linking the two products through the function h. So this is what we mean by saying that h preserves the product. As to the unary operations, we have this equation. So we can, for any element of W1, apply the unary operation lambda 1, then apply our function, or first apply the function, then apply the unary operation lambda 2, and we get the same result. So this says that the function h preserves the unary operations. Finally, as to the nullary operations, h must map E1 to E2. That's preservation of the unary operation. Structure-preserving functions between widgets are called morphisms. And there are morphisms in many different branches of mathematics. Continuous functions are morphisms in the correct setting. Differentiable functions are morphisms in the correct setting. And there are many other cases. But in abstract algebra, we have group morphisms, ring morphisms, field morphisms, vector space morphisms, module morphisms, lattice morphisms, monoid morphisms. But each of these has a more specific terminology. You won't hear the word morphism used very often outside of actually category theory, where that's the common term. Group morphisms and ring morphisms are called homomorphisms. Field morphisms are called embeddings. Vector space and module morphisms are called linear transformations. Lattice morphisms are also called homomorphisms. So you have group homomorphisms, ring homomorphisms, lattice homomorphisms. Morphisms are so important in mathematics that an entire branch of mathematics was developed in order to elevate or make it clear that their importance is on a par with the importance of the structures themselves. So group homomorphisms are just as important as groups, and ring homomorphisms are just as important as rings. You can't do group theory without group homomorphisms, for example. This branch of mathematics is known as category theory. A category is essentially just a collection of objects along with their morphisms. There's another extremely important common theme that we should mention, because it too is used not only throughout algebra but throughout mathematics. And this is the technique of representation. Oftentimes, a great deal can be learned by representing one type of mathematical object as another type of mathematical object. Now that's a very general and vague statement, so let me give you two examples. A real number, little r, can be thought of not only as a real number, of course, but also as a function. So it can be represented as a function. And the function is multiplication by r, which I will denote by mu sub r. So this is what the function looks like. It's a function from r to r, and it is multiplication on the left by r. Now, since multiplication of real numbers is commutative, it doesn't matter which side we multiply, but speaking or thinking more generally, this will apply to products that are not commutative as well. So there we have to make a distinction between left and right multiplication. This function, mu sub r, is bijective when r is not 0, and it's referred to in some contexts as left translation by r. Sometimes one thinks of translation as meaning addition, but that's not necessarily the case. Note that if we know this function mu sub r, we can easily recover r just by applying mu sub r to the element 1. So knowing mu sub r is equivalent to knowing r. So in a way, it's just a different point of view looking at real numbers, looking at them as functions. And we're going to generalize this idea and the left translation representation to arbitrary groups much later in the course. Here's an example that you are probably familiar with, although not in this language. In elementary linear algebra, we think of matrices, such as, for example, this 2 by 2 real matrix, not just as rectangular arrays of numbers, not as formal, static tables of numbers that can be added and multiplied together, so we have matrix algebra, but also as something that's alive, that does an action, and that is, we think of them as linear transformations, multiplication by m. So for this matrix, this would map R2 to R2, and here's what it would do. The role of matrices as linear transformations is critical in linear algebra. And in fact, if you took my linear algebra course, you may remember that I actually incorporated that into the definition of a matrix. The columns of a matrix tell us what happens when we apply the matrix to the standard basis vectors. And so a matrix is not just a static array of, say, real numbers that we can multiply and add, but describes or defines a linear map by defining its action on a basis. And that's all part of the definition of a matrix. And that's the way I encourage students to think of matrices in linear algebra. Speaking in general terms, a representation of the elements in a widget A by the elements in another widget B, and B is often a different type of widget from A, is defined by a function, lambda, from A to B. I know I've used lambda in the past to represent unary operations, but this is a different context and we often reuse symbols. So this is called a representation map. And an element little a in the first widget, capital A, is then represented by the element lambda of A in the widget B. Sometimes this is denoted lambda sub A rather than lambda of A. And sometimes, as we will see when we get to this much later in the course, sometimes the representation is also denoted by the letter A. At first that's going to be a bit confusing, but once you get used to it, it shouldn't be too much of a problem. Another thing that you may be wondering is it necessary for the representation map lambda to be injective? That's certainly desirable because that means two different elements of A will be represented by two different elements in B. Such representation maps are called faithful. But it's surprising how often a non-faithful or unfaithful representation, a map that's not injective, can still tell us a great deal about the elements of A. Obviously, if lambda mapped every element of A to the same element of B, that would be pretty useless. But still, representation maps that are not injective can be very useful. Finally, in this lecture and in this chapter, I want to discuss something else. And this is something that you will probably not see anywhere else, at least not articulated in this way. It's this concept that we're going to discuss, which I call the extreme witness principle, is used throughout mathematics and very heavily in abstract algebra. But I have not seen anyone else articulate it directly in this fashion. The reason I'm doing it is because I have used the extreme witness principle, as everybody does, many times in this course and in the other courses. But when I was writing the most difficult proof in this course, in the group theory lecture series, it has to do with the structure of finite abelian groups. The proof, I've never seen a proof I really liked, and I struggled with trying to construct a proof that is motivational. This is the problem with the proofs that I know of for this particular result. It's very difficult to look at the proof and say, I see the thought pattern behind it. I see how someone might have discovered the ideas in this proof. They seem to come out of a hat. More appropriate to say they're strokes of brilliance that nobody really can explain very well, I guess. Now maybe I'm missing something, but that's the way they feel. That's the way these proofs feel to me. So I struggled and rewrote the proofs that I've seen multiple times. The ideas in the proof are not mine, they're other people's that came before me. But I wanted to rewrite the proof in a way that I thought would be the most insightful or motivational. And what I discovered was that while I can't necessarily motivate the entire proof, I can motivate pieces of the proof. And the pieces that I can motivate, the motivation is the extreme witness principle. It's used 3 times, if I recall correctly, in the proof. And so that's the point at which I said to myself, I think it would be a good idea to discuss this briefly at the beginning of the lecture series. So you will recognize it as it comes up. I think it comes up something close to 12 times throughout the course, so it's quite a lot. So here is what it is. Speaking in general terms, in mathematics, we will often encounter a family F of mathematical objects that are defined by some property P. For example, the family of spanning sets of a vector space. This is the family of all subsets of the vector space that are characterized by the property P of being a spanning set. The set of all continuous functions on a set. This is the family of functions on the set that are characterized by the property of being continuous. So there are many cases where this is the scenario. Now, we often want to find a specific member of the family that possesses an additional property that we want. Call that property Q. Also, perhaps we just want to learn more about the family. We've defined a family of continuous functions. We want to study that family. In this case, if the family is ordered in some natural way, such as by set inclusion, by dimension, by degree, then it is often wise to look at the members of the family that are extreme with respect to that order. And that generally means the largest or the smallest, or if those don't exist, the maximal elements or the minimal elements under the order. And I wanted to give that a name. So here is the official definition. Let F be an ordered family of mathematical objects that are defined by some property P. Suppose we wish to find a member of the family that possesses an additional property Q, or simply learn more about the structure of the family. Then a good starting point is to examine the extreme members of the family. This is an ordered family. So extreme members with respect to the order, which we will call extreme witnesses to the property P. And accordingly, refer to this principle as the extreme witness principle. So again, this is a very general idea, probably pretty vague, but let's look at an example. Suppose we've just embarked on the study of vector spaces. So we know the definition of a vector space, we've figured that out, and we don't know much else. Then we stumble upon the notion of a spanning set. Seems like a good idea. If we want to learn more about the family I called script S of all spanning sets for a vector space V, we examine the extreme witnesses for this family. The family is ordered by set inclusion. There is a maximum member of the family, a maximum spanning set. It's the vector space itself. That's not going to get us very far. On the other hand, the minimal spanning sets, there are also extreme witnesses, extreme to the other, on the other side, these are extreme witnesses to the property of being a spanning set. And they're very interesting, aren't they? Because they're the bases for V. So by examining the appropriate extreme witnesses for the family S of all spanning sets, we are led in a natural way to the notion of a basis. Similarly, if we had first stumbled upon the notion of linear independence and wanted to learn more about the family, which I'll call script I, of all linearly independent subsets of a vector space V, we again turn to extreme witnesses. The minimal extreme witnesses, the minimal linearly independent sets, are boring. They are the singleton sets consisting of a non-zero vector. They're not going to tell us much about linear independence. On the other hand, the maximal linearly independent sets, and they're also extreme witnesses to linear independence, they are, again, very important because they're also the bases. So the bases for a vector space are precisely the appropriate extreme witnesses in either of these two families. And we are led then very naturally to the notion of a basis by applying the extreme witness principle to either family. So that's an example. And we, as I said before, will have several occasions, many occasions, to use the extreme witness principle in this book.